Am I audible in the back? So, am I audible? Clear, eh? Okay. So, what were you doing in the last class? Okay, in the last class, you're looking at the bump that gets generated on the internal node of the memory cell when you are reading a 0. And after that, we looked at the writability aspect also. So, what are the key things that we looked at when we were looking at the bump there? So, why does the bump get generated? Because of a potential divider configuration that gets established between the bitline and the ground. If you want to reduce the bump, obviously, if you reduce the level of the bitline, the bump would reduce. But we wanted to look at what other mechanisms can we bring into picture so that we can reduce the bump there. Are you with me? And for that, we looked at one of the most important cell design parameters, which is cell ratio. We said that pull down being greater than much larger, less resistive than the pass gate is a very key determinant of the bump that will appear. And then as we added more variables, for example, variables linked to mismatch, different voltages going up, down, all those things, as we started to do that, what did we observe? Many of those gains were getting eroded also. Are you able to see this? And then we said, okay, if those gains of cell ratio are getting eroded, how do we recover? And we looked at various read assist schemes. What were the read assist schemes that we ventured into? We looked at wordline underdrive. What is the challenge of wordline underdrive? It degrades writability, but for the read operation itself, even when suppose you say I will not do a wordline underdrive during write, then is there no disadvantage? No, even then there is a disadvantage. As you underdrive the wordline, what happens? Cell current goes for a toss. And cell current is a very important figure of merit during read operation itself. Is it not? So wordline underdrive helps me gain stability, which is linked to the read operation, but it also degrades the cell current, which is a performance figure of merit linked to the read operation itself. See, if it was like कि अच्छा खाली write पे ही impact होना है, तो बड़ा simple था ना. You already have some information within your memory कि भाई ये read cycle है कि write cycle है. All you need to do is put a logic design. All of you have done so much. First year se leke, even in DVD course, all that we were doing was logic design. It was too simple. That is not where the challenge is. The challenge is that When you are improving a functional figure of merit related to read operation, the performance figure of merit linked to the same read operation goes for a toss. Are you with me? Yes.
The wordline underdrive would lead to slower read access, right?
Yes, because the read current would reduce.
Yes.
Then what was the other figure of other read assist scheme we looked at? It is a read assist scheme because it is improving the stability. Assist schemes could be used to improve both functionality and performance or power. Anything that we use to change and recover more can be called as an assist scheme. So it's a read assist scheme because it improves the functionality, but it degrades the performance. The other read assist scheme that we talked about was negative VSS. What is the outcome of negative VSS? Okay, when you reduce the VSS, what happens? Effective voltage across the pull down increases. As the effective voltage across the pull down increases, you need lesser VDS, or let us say VX reduces. And SNM improves.
The cell current would also rise, right?
Cell current will also improve. So what is the disadvantage here? Stability is improving. Yes. Now there is a penalty on area. You will need additional charge pumps to generate these negative voltages. Or you will need to have two extra or at least one extra supply, a negative supply routed through your entire memory array so that you are able to get a successful read operation. So read assist schemes, in fact, all assist schemes could have some penalty because they are improving one functional parameter or another, or a performance parameter or something else. They may have an impact on something else somewhere. That is the complexity of SRAM design. Are you with me? Any questions until here? So we know of, abhi tak, we know of at least three read assist schemes. First is bitline lowering, which is pretty obvious. Second is wordline underdrive. Third is negative VSS. Now, this negative VSS can also be considered as VDD boost scheme. Are you able to see this? VDD boost will lead to exactly the same things. Something is acting on the PMOS, something is acting on the NMOS. The gains may be more or less. But negative VSS का dual ही है VDD boost. Again, challenges have more charge pumps to boost the VDD when needed. All those things are there. But VDD boost is also like that. Are you with me? Now, this VDD boost scheme can be very useful. When can it be useful? For example, I say that I want to reduce the power. I will separate the power supply of the array only. Now, the array operates at 1.1 volts, but periphery can operate at 0.8 volts. At 1.1 volts or 1.2 volts, wherever we did the experiment, there was sufficiently good SNM. At that particular voltage, there was also sufficiently good read current. So speed is there, stability is also there. I am operating at a higher voltage. Now, if all the arrays are going to operate at a higher supply, it may be worth to put a small voltage regulator, not a charge pump, a small voltage regulator somewhere in the chip. Interestingly, array doesn't consume any power. What power does array consume? Nothing. See, bitline pre-charge power comes from the IO. Array only charges up the internal node of the memory cells where something needs to go to 1. Look at the array supply. Where is it used? Only that place. Otherwise, it is only leaking. It is only there to maintain whatever the contents were there. So the voltage regulator that you will need to design in such a scenario will not be huge. And now you're saying it is shared across all the arrays on the chip. So by sharing, now again, ध्यान रखना, sharing से आप हमेशा costs को optimize कर सकते हो. By sharing that LDO, that voltage regulator across the entire arrays, you also reduce the area penalty of generating that boost. Are you able to see this? So we've not specifically talked about it, but do you realize that that's a simple extension of what we have discussed in the class? It is such extensions that you will need to think of and do as a designer. In your jobs, wherever you go. Do not think that these book solutions or the ones that what I'm telling you are not book solutions. You will not find them in any book. But these are still, basic. I'm giving you building blocks. You have to learn how to create that building when you join your jobs, when you start to work on your projects. That is where your innovation comes in. That is where your creativity comes in. That is where you add value where AI cannot. Are you with me? Because I'm only increasing the voltage of the memory array. But are they consuming current? They're all leaking only. लीकेज बढ़ेगा, बट एनीवेज आप जब वर्ड लाइन वीडीडी को बूस्ट करते तो भी तो लीकेज बढ़ता है, आप डायनामिकली करते तो भी तो बढ़ता है. नाउ इट्स अबाउट what cost am I ready to give in the leakage? See, I can say that because I'm operating at 1.1 volts now, I will use HVT devices. If I was to operate at 0.8, obviously I could not have used HVT devices. So by going to a higher voltage, I have also more flexibility to reduce leakage by other means. I can still say that during standby, I will go to the periphery supply so that leakage reduces in standby. There are so many things I can think of. Are you with me? So this is about you extending whatever building blocks I have given you in the class to arrive at ingenious solutions. If you limit your understanding to what we are discussing only in the class, okay, you will get a job, you will do something. But if you really want to shine, you have to realize that these are just building blocks. You have to use them like Lego. Is it okay? So what was the next thing we looked at in the class last class? It was writability. And when we looked at writability, we saw that ab yahan pe, unlike in a read operation or a read stability thing, we need to look at the entire latch. Because that Vx that gets generated because of read operation has a significant role to play in the pull-up to PG ratio that I have to maintain. If that Vx was not there, then my pull-up is going to be far stronger and my PG has to be much bigger. There is a huge area penalty that I will end up with. But because of that Vx coming in, which was a devil just a little while back, but in the right operation that is helping me gain density. Are you able to see this? So, and that was also the reason why we estimated Vx before we estimated the Vint, or how much I am able to discharge the one node during the write operation. This was a question one of you asked. Because I need Vx for density purposes and for memory cells, area is diamond. Memory cells, nahi, memory's area is diamond. Okay, so we calculated Vx first, then we came to Vint. Is that okay? What are the write assist schemes we looked at? So now you see they are completely opposite of what we looked at for read. वहां पे हमने कहा wordline underdrive, यहाँ पे हम कह रहे हैं wordline boost. So when you do wordline boost, the unselected cells in the same row will struggle with stability issues. So you have to go to MUX1 only. MUX1 means that your aspect ratio is going to be bad. The largest number of words that you can have in the memory will have to be limited. So you'll have to juggle with so many other complexities. Okay. What else could you do? Okay. वहां पे हमने कहा हम array supply को बढ़ाएंगे to gain stability and improve read speed. यहाँ पे we can lower the array supply to just the array supply to improve writability, make the pull-up weaker. Write speed will still go for a toss. Are you with me? When I do that, write speed will still go for a toss, but we can do it. Third thing we discussed was raising the ground level. वहां पे हमने कहा था ground को negative ले जाओ, या हमने कहा कि array को नीचे कर लो. That also means यहाँ पे ground को आप ऊपर ले जाओ. As you raise the level of ground, you kind of make the cell unstable. As you make it unstable, you can write into it. But now you cannot, the ground is shared across so many cells. Ground, we did the layout of the SRAM cell first. Why? Because now you know that the same via that gives you ground is shared across 4 cells. See, the way we are flowing through the class, there is a reason behind it. I could do the layout even now, na? I could have talked about these things. But then you would not be able to appreciate that the same, अगर मैंने बस हर ground rail को अलग-अलग भी touch करा, तो भी as soon as I say ground को raise करो, 4 cells come at risk. I want to write only into 1. यही जब मैं VDD को lower कर रहा था, VDD is shared across 2 cells. Are you able to see this?
So how is the write time degrading when we lower the array voltage? Is it because for the left side where we are writing 1?
Where we have to write 1, over there VDD is low. Now the pull-up doesn't have the drive, the gate overdrive, to get the right current to be able to write a 1 there.
But writing 0 is faster.
Writing 0. Yes, you have already done that. Writing 0 is faster. Now, you remember we talked about bitline not being at VDD so that we can gain more stability. One very interesting and very important write assist scheme is negative bitline. Why is it more powerful than ground? Because bitlines again are shared only across 2 cells. Bitlines, even if they are shared for other cells, the pass gates are off. They do not impact the latches inside those cells. See, जो ही आपने ground को touch करा या VDD को touch करा, latches of all the other cells in the same row or the same column are going to get impacted. Bitlines are not coupled to every memory cell. They are coupled to only that memory cell where you want to do the read or the write operation. So only your target cell gets impacted with whatever you do on the bitline. Again, you have to know the layout to be able to appreciate this. Are you able to see this? And then you say that negative bitline is a very powerful write assist scheme. Because what you can do, okay, you wanted to take vint to a lower level and your write driver was until now able to take it only to 0. Now you say write driver will take it to minus 100 millivolts. So now it cannot take it to minus 100 millivolts, but जो भी वो vint आना था वो minus 100 के बेस पे शुरू होगा ना कि 0 के बेस पे. So your internal node for that particular cell will be closer to 0 than it was in the earlier case. And what do you need to do? You need to make a write driver which is able to generate that negative voltage. So there is a small charge pump we can put inside the write driver there. Are you with me? So in terms of write assist, negative bitline is the most commonly used write assist scheme. All these will help. But in your calculations, just change the value of VBL to a negative value and you will see, oh, a lot of gain. A negative bitline thing, because it helps me to take internal node closer to 0, will also turn on the PMOS on the other side well. So it does not degrade write time. In fact, it improves write time. Are you able to see this? So because it does not touch the core of other cells either in the same row or the same column, and because it improves both the functional figure of merit and the performance figure of merit linked to write operation, negative bitline is a preferred solution. But ये क्या हो गया? अभी तक तो सर कहते थे there is no free lunch. यहाँ तो लग रहा है पांचों उंगलियां घी में, सर कढ़ाई में. So what are we losing? Area, but yeah, it's okay. Okay, that is something. See, in terms of devices, now, will you always operate the memory at, let us say, 0.7 volts or 0.8 volts? No. We know about DVFS already. We know that there will be times when I will need very high speed. So in those times, I will operate the memory at 1.2 volts. Am I right? So at 1.2 volts, when I'm operating the memory, what happens? This negative bitline may still get generated. Now, look at the pass gate. The word line is at 1.2 volts. Bitline is at minus 200 millivolts. What is the VGS? 1.4. The safe limit of VGS is 1.3. At 1.4, the gate reliability issue comes in. Dielectric breakdown can happen. So now as a designer, you have to ensure, again, either through combinational logic or through other stuff, that when I'm operating at 0.9, I get only 150 millivolts of negative voltage. When I'm operating at 1.0, I get 50 millivolts of negative voltage. And when I'm operating at 1.2 or 1.3, I do not get any negative voltage. So I have to make it programmable now. And it is not simple because do you know the principle how charge pumps operate? They amplify whatever voltage you're operating at. Whatever the VDD minus VSS you have, they kind of amplify that in some way. A fraction of that they will amplify. So you wanted 200 millivolts to be generated at 0.8. So you wanted a boost of 25%. You design a charge pump with 25% boost. But at 0.9, you said, now I don't want 25%, I want only 12%. At 1.0, I want 5% only. So your charge pump design is far more complex than what meets the eye. See, again, देखो, यहाँ पे system view कितना जरूरी है. If I'm in a very myopic way, looking at only this small problem, oh, 0.8 पे या 0.7 पे मेरा writability खराब हो गया, उसको ठीक करना है, तो negative bitline, yes, बल्ले बल्ले. But am I going, now system view tells me, no, that is a very partial view. I need to operate at high voltages also. What will you do then? There will be gate reliability issue that comes in. Are you able to see that any design? See, do you realize this is a high-level course? This is no longer one of those core courses. This is an elective course. So in this course, I am giving you far more information, knowledge, advice, empirical rules than what you have been used to handling until now. This is not like DVD where I was just keeping one level taki sabko, there is a person who is doing this course only for the sake of mandatory course hai. This is an elective course. You come here because you choose to come here. This is a 6-level course, which means PhD students also will be here and they have to utilize information of this place into their research. 6-level course also means that when master students or whoever is coming to this course, they should be able to think like an expert now after this course. So if there are other 6-level courses where you're not taken to that level, you should challenge the instructor. But over here, what I'm saying is that in this 6-level course, we are going to talk about things which are beyond common knowledge. And you need to realize that any design is not just about that circuit or the voltages operating in that circuit. Every design operates in a context. And the context for this memory cell design is the context of a memory, the context of an application, of an SoC where this is going to operate. If you keep a very small view, zoomed in view, keep a memory cell, then you're operating at the level of a 300 or a basic level course, a mandatory core course. I want you to think big. Big means, वैसे big नहीं, memory has to be very, very dense. Okay? But I want you to think beyond the boundaries of just this one topic. And this is a skill that you need to develop whatever you are doing. Whether you are designing a product in CIPD or you're doing computer architecture stuff, whatever you are doing, you have to look at multiple contexts when you arrive at solution. Otherwise, your solutions will be half-baked. They will remain within the academic literature and not see the light of the day. You will never be able to approach a place where a company would say, okay, I want to file a patent on this topic. I want to hire you because you have this kind of a thought process or a knowledge there. So systems thinking is very important there. Is that okay? So now we start with ROM cells. Yes. Sorry. दोबारा से बोलो. Oh.
Observation from that equation.
No, you can always reason it. Look at it like this. All currents that are going to flow in any system, any device, are in some way dependent on VDD minus or VGS minus VT.
Yes.
Now, what is VGS? VGS has some semblance of VDD in it. है ना? Gate पे VDD लगा है, source पे 0 लगा है, तो VGS is mostly about VDD. Has a semblance of VDD in it. I would not say VDD, but a semblance of VDD in it. And from this VDD, you are reducing VT. That is what is going to define your current. So if you increase the VT, it is as good or bad as lowering VDD by that much voltage. Are you with me on this? So whatever you were able to observe at 0.8 earlier, with higher VT, you will start to observe it at, suppose 50 millivolts higher VT, you will start to observe it at 0.85. Are you with me? So as you increase VT, all the behaviors of lowering of VDD will start to become evident. Is that okay? You will reduce leakage, yes. But everything else will also change, na? Because it is about VGS minus VT that all these equations are dependent on, saturation equations are dependent on. Is that okay? Any more questions? Yes. So his question is कि negative bitline voltage की जो आप बात कर रहे हो पहले 0 तक discharge करते हैं फिर उसके आगे जाते हैं. Yes. So you have to, now that is a design complexity, but we are okay with design complexity. Look at it, ना हमने वो 14 transistor D latch को 6 में convert करा and we said we will take care of all these read margin, write margin, blah blah blah, all these so many figures of merit. We are agreeable to take care of them. Why? Because area is diamond. So because I can make my memory cell denser by using this kind of a write assist technique, I'm ready to add more design complexity in my system. Okay. Now, as soon as I add more design complexity, I also have to test more. There could be other delays, costs, margins that I need to take care of. But as designers, you're ready to add more complexity into the design until area is diamond thing is maintained or enhanced. Okay. So what you need to do is you need to have some timing or some kind of a replica where you say that, okay, my bitline has gone to 0 now. by the write driver. And after it has gone to 0, I will now take it to a negative voltage. And then when the precharge starts, it will go back up. So this, because if you trigger that charge pump somewhere here, what was the role of the charge pump? Minus 200 millivolts leke jana. Now, if the bit line is at, let us say 100 millivolts, then minus 200 from 100 is only minus 100. Your design may fail. If you do it much after this point, then you have wasted so much time. That is, performance has gone bad. So you want to bring this lowering as close to bit line touching 0 as possible. It's not simple. It requires design creativity, but you have to do it, and we'll do it. This is a part of write driver design. I don't think we are going to touch that today, but we may. So when you design the write driver with the negative bitline assist voltage, write assist scheme in there, you have to take care of this. Are you able to see it? So now we want to close the memory cell part of the game. So we talk about ROM cells. We already talked about ROM cells earlier. We've talked about the programmation layer and all those things earlier. So we'll move a little fast today. Is that okay? So ROM cells, there are two kinds of ROM cells that we are talking about: NOR-based ROM cells and NAND-based ROM cells. And what you need to notice over here is that you see there is, as of now, none of the transistors that I have put here are connected to the bit line. Word line comes, none of the bit lines discharge. Are you able to see this? But now I have put some connections. When the word line comes, depending on what was stored somewhere, bit lines would discharge. So what have I done? By creating that bit line to a ROM cell connection, I have written something into the memory cell there. And this connection could be a metal one, could be a via, could be a contact, all that we discussed already. So उस समय आपको समझ में नहीं आ रहा होगा contact से programmation करते कैसे हैं. Now you understand, if the contact is not there, then the bit line is not connected to the cell. Or if I'm doing metal 1 programmation, then let there be a contact, let there be a via 1 also, but there is no metal 1. So no connection happening. So metal 1 programmable. Or let there be a metal 1 also, and let there be a metal 2 bit line also. There is no via 1 that I put. So how you do this is the metal layer at which you are programming. But what are you doing? This is a NOR structure. That word line comes and immediately the bit line discharges. Now, what are the challenges in this? So what is the benefit of this? Word line comes, bit line discharges, speed. NOR, you will always see, whenever we talk about NOR kind of a structure in memories, we are doing it for speed. Okay? What are the disadvantages? See, when you do this drain programmation, there are some bit lines which have no programmation on them. There are others which have programmation on them. So bitline capacitance is going to be different. Suppose I have a bitline which has the minimum kind of a capacitance, but it is right next to another bitline which has a discharging cell. Now the coupling capacitance will ensure that this particular bitline, by the virtue of coupling, will start to discharge. So I have created a hell for me by changing this bitline capacitance. Yes, bitlines which have lower capacitance will consume lower power, less power, probably. Okay, but it doesn't really help me because I have to design my cell timing for the worst case cell only. So even if that bitline was lesser capacitance, it will discharge more now. because my word line is going to be on for the required duration. So जो seemingly power का gain दिखता है कि capacitance कम करा तो power होगा, that is also not there because now I am discharging it more. The delta V for which this bitline will discharge will be more. Because power is not a function of bitline capacitance in the memory array. In the memory array, power is a function of the duration for which word line is on. Are you able to see this? So your memory cell is in saturation. It's like a current source. It is sinking some current. Now the duration for which this one is connected to whatever capacitance is going to determine what is the charge that you sunk. Whatever voltage this capacitance stored, is that important? No. You have a current source. It is in saturation region. You change the VDS, doesn't matter. Current will remain almost the same. Are you with me? So even if my bitline capacitance is smaller, doesn't lead to power gains. Though it appears, अरे capacitance कम हो रही है, power gain होगा. In reality, it doesn't. Again, look at the context in which it is operating, how it is operating. So what have I done? I might think I have reduced bitline capacitance. It would lead to something good for me. But you anyways have to design for the worst case. So you have to keep the word line on for the worst case duration. The bitline will only discharge more. But the charge that you have to replenish is going to be the same. So no gain in power, but much more increase in complexity. Because now all these variables of what kind of a coupling capacitance would come, what could be my worst case, all those things you're going to struggle with. So what you do then is that you, instead of, so वहां पे देखो, वहां पे हमने क्या करा था, इस वाली नोड को floating छोड़ा था. Over here, what we've done, we have left the ground side unprogrammed. Wherever you want to store a 0, you put a connection there. Now again, this could be via 1, metal 1, contact, whichever way. When we say diffusion, when we say ROM D, what that means is the active doesn't exist. There is a contact, there is a poly, but the active is not there. So the transistor is not there. Okay. But when you have either of contact, metal 1 or via 1, then you have to worry about whether you are doing the programmation on the source or on the drain. If you're doing ROM D, that is ROM diffusion, then the diffusion doesn't exist, then doesn't matter. Because then source पे कर रहे हो, drain पे करो, device तो आ ही जाएगा. That वहां पे तो capacitance variation आना ही है. So ROM D is not preferred because of two reasons. One, that it is diffusion layer programmable. Second, that even if you do source programmation or drain programmation, you cannot now control the bitline capacitance. It is going to be very, very variable. Are you able to see this? See, if you say that, okay, my connections towards source and drain were always there, just the transistor was not there, then you have come to the same earlier loop, na? That as soon as you want to put a transistor to program a 0, the capacitance will change. Now the drain capacitance becomes visible, otherwise it was not there. So ROM D is not preferred because of two reasons. Is that okay? So over here now, even if there is a change in the programmation across a column, my bitline capacitance remains same. It is much more deterministic, and I can now handle things in a better way. Is that okay? Now let us look at the NAND cell. What is a NAND cell? Why is it called a NAND cell? Because now we are saying that it is not just one transistor and which is connected to ground and bitline on each side. It is now a stack of transistors. Are you with me? It is a NAND kind of a stack, and therefore it is called as a NAND ROM. You're able to see the NAND kind of a stack here, na? It's a stack of 3 NMOSes, just like in a NAND structure. Now, what is happening here? Bitline is not connected to every program cell. Bitline is connected only at the top of the stack. At the top of the stack, I have clock going. Only when the clock comes, my bitline will discharge. This clock can be at the bottom of the stack also, but wherever. Okay. Now, how do you program? You program by shorting across a transistor. But what this means is that unlike in a NOR cell where wordline selection meant wordline will go high, in a NAND cell, the word that you want to read, for that, the word line will remain low. Those of you who have not watched the lecture already, you would not understand it immediately. I will just take you through that. So, I'll have to do it there only. Look at it over here. In the first column over here, let us say you wanted to read the word 0. The word line 0 was to be selected. If word line 0 is kept as 1 during selection, what would happen? Let us say word line selection means word line is high, the unselected word lines are low. Let us say. So what will happen? Clock came, the top NMOS went on. You wanted to read word line 0, so you took word line 0 to 1. As soon as you took word line 0 to 1, what happened? All the cells on the word line 0 are now on. What is controlling the bitline discharge? See, word line 1 is 0. What is controlling the bitline discharge? The programmation of which cell? Of the cell on word line 1. The first 2 columns will discharge. The next 2, because word line 1 is 0, they will not discharge. You wanted to read word line 0, but you're reading word line 1. So, in a NAND cell, you will read that word line which is meant or which is kept at 0. And you have to keep all the other word lines of the same cell high. They have to be maintained 1. Are you able to see this? Any questions? We have flipped. Flipped means not data flip. We have changed the way word line is to be handled. The state machine will change. Your control block will change. Are you able to see this? As you transition from NAND to NOR gate or vice versa, your control logic changes completely. Unlike a transition from 60 to 80 or a smaller high density 60 to a high current 60, things are very different now. It's something like आपने pass gates को NMOS की जगह PMOS कर दिया तो हमने कहा oh now the bit line will be pre-charged to 0 and word line will be active low and so many things we talked about when we were talking about the 60 memory cell. Are you with me? So similarly, when you transition from NAND to NOR or vice versa, the way you handle your word lines changes. Your state machine changes. The control logic changes. Is that okay? And what are the advantages of a NAND cell? They are denser. Disadvantage, they have lesser current. It's a NAND stack. Versus that they have lesser current because, see, even when I turn on, suppose I unselected word line I have kept high. So all the transistors there will conduct current now. Are you with me? Now, even if I have kept the word line high, do you realize that every transistor has some on resistance? Even if it is 10 ohms, even if it is 20 ohms or 100 ohms. See, what are we comparing? 100 ohms versus 10 kilo ohms. Order of magnitude of on resistance versus off resistance is very, very high. But there is still some on resistance. Are you with me? But where you had programmed For that particular device, because there is a metal in parallel to the SON resistance, there is no resistance. Are you able to see this? So what this leads to is that now, even though you want to read 0, the bit line should discharge depending on what was written in the same stack. My current could be different. Are you able to see this? So what I'm saying is that, let us say there are 2 bit lines. Let us say there are 2 bit lines. This is the word line that you are keeping low. This remains low. The other word line goes high. Let us say the first bit line, there was a short there. The second bit line, it was programmed as 1. Okay. So now what is the equivalent resistance of this one? There is a R on of C eval, CK eval. There is a short. And then there is, suppose I had done this. There is something that is going to, I had not selected this. So the current has to go and this is a short. So it will be like this. I have a resistance of RCK there. Look at the other cell. There is RCK. There is RM1. And then it goes to ground. Are you able to see this? So you had some particular voltage over here. Do you realize now the current that the 2 bit lines will sync is going to be different? That is a source of variation for you, a systemic source of variation for you. Which means that you have to margin for all the possible combinations that there could be. So यहाँ पे मैंने just 2-bit cell दिखाया है. तो एक ही combination possible था. Consider I say that there is a 4-bit cell. 4-bit cell का मतलब there are 16 NMOSs in stack. Are you with me? 16 not in stack. 4-bit means 4 in stack. But there's so many NMOSs in stack. Now all the combinations you have to see. And all those are variations in your read current now. Over and above the device variations that are anyways going to be there. NOR में ये सिदर्दी नहीं थी. NOR में it was always one transistor, and if it was conducting to ground. Same current. Only device variation was coming. In NAND, you need to take care of programmation related variations also. But since it is denser and in memory's area is diamond, NAND flashes also, NAND ROMs also are preferred. Is that okay? NAND are preferred. But when you want speed, you have to go to NOR. Then there is no other option because NAND will degrade the speed. When you design, na, वो तो काम तो designer का है. See, always think of it like this. It is your role to ensure that there are sufficient margins wherever there need to be. But area is diamond. You are getting a salary because you have to ensure this, that this works. Got it?
Also, sir, I was not able to visualize how NAND cell are more denser than the NOR. Like we are even using the extra transistors of clock.
So what happens is now you have to think of it in terms of layout because you're talking about density. In a NOR cell, you will end up putting more contacts because there are more ground nodes, more things coming in. In a NAND cell, this node may not have a contact at all or no DRC spacing required at all. In a NAND, in a NOR cell, you have to create those DRC spacing between two cells so that इधर bitline का contact आए, उस तरफ ground का contact आए and whatnot. But in a NAND cell, you don't need to keep all those spacings. So NAND is denser. This will become far more evident when we touch flashes that NAND architectures are far denser. वहां पे तो प्रोग्रामेशन के लिए ये भी नहीं करना होता ना, यहाँ तो आपको कॉन्टैक्ट डालना पड़ रहा है फॉर प्रोग्रामेशन. We're only talking about DRC spacing, but in Flash, you program in a completely different way. So you will see that the benefit or advantage of using a NAND flash or a NAND structure in the non-volatile cell will be very, very prominently visible to you. Is that okay? So with this, we are kind of closing the chapters on memory cells for SRAMs and ROMs. Okay. This is then also the right time for you to start thinking about your projects. आप सबकी project teams बन चुकी हैं, बना दी हैं आप सबने. So start to think about projects also. Depending on what you choose for projects, you may also want to choose something for some papers that you want to read for your assignment and all that. So those instructions will start to follow onto the Google Classroom, but start to think on those lines. If you're not able to come up with a project idea yourself, we'll also share with you some titles that you can work on. Again, realize this is not a core course now. This is an elective course. You have much more freedom here. Is that okay? We're not binding you. But if you need help, we will give you some props to guide you. Now we come to I/O. Okay. What is the purpose of using an I/O in a memory cell, in a memory array or a memory? Huh? Someone said read data, write data.
So you don't
Taking output. Okay.
so you don't want the end user to have to control everything. You want that some level.
You want convenience for the end user somewhere.
Decodes the memory cell charge to what actually.
Decode the memory cell charge, whatever. So see, dekho, when we move from that 14 transistor D latch to a 6 transistor cell, we already started that with the premise that, for example, we said that one NMOS will go down there and we will call it a write driver. We already said that just to operate that cell is not a complete storage element in itself. I need some additional circuits to make it complete. Are you with me? So you already established the need for an I/O right there. Now you also established the need for a row decoder. We will come to that also, because you said all the memory cells will be placed adjacent to each other, organized in rows and columns. So establish the need of a row decoder also. We are starting with I/Os because I/Os already contain components of the memory cell or the storage element. Are you with me? So in an I/O, there are some things which are definitely going to be there. So in an I/O, you're going to have bitline p-charge. You're going to have column multiplexers. You're going to have sense amplifiers. On the read side, the output of sense amplifiers needs to be buffered, so output buffers. On the write side, you have to have input buffers and write driver. Are you with me? If you really want to take it to the bitline level, then जहां पे हमने column mux कहा, column DeMUX भी आप कह सकते हो. We basically make one circuit which acts as both mux and DeMUX. We call it column decoder. But you could also call it column DeMUX. Or you can say that if I do not give it both the functionalities, then I need something for the write operation also. Because for us, area is diamond, we don't want to waste area. We say, okay, this one circuit will do both the jobs. But it is needed. An interesting thing is, right now also you have to decide where to place the mux. Should the mux be placed before the sense amplifier? or after the sense amplifier? Where should the write driver be? Should it be after the MUX or before the MUX? It depends on the requirement. For example, if I put the MUX after the sense amplifier, what are the advantages I could get? Now my sense amplifier will see fewer resistances from my bit line or the cell which was discharging the bit line until the sense amplifier. So I could be able to sense at a lesser differential. What is the disadvantage? Area. Now for every bit line, I have to have a sense amplifier. If it was after the MUX, what happened? I could have only one sense amplifier for all the bit lines that are entering into that MUX. Similar thing would happen for the write drivers. Are you able to see this? If I put it above the MUX, I would have write driver for every bit line. If I put it beneath, I have to have it once. The advantage of putting it up there is that whatever negative voltage I generate, so you already talked about negative voltage just now. Whatever negative voltage I generate, that will be fully available to the bit line. If I put it below, then I know that some of that negative charge will get dissipated towards the sense amplifier, towards many other things that are there in the IO itself. So I have to have a bigger charge pump. Or I have to have a design which is taking care of all these aspects. So you could have the multiplexer down there with the write driver up there or the sense amplifier up there, but each one of them has their own disadvantages. Okay? Now what we will do is we'll quickly look at various components of an IO. The first circuit we look at is precharge. This is static precharge circuit. The PMOSs are always on. What is the challenge with this? Static power, yes and no, in the sense that you will not call it static power. What you will say is that this PMOS is always on. So when your word line comes, bit cell has to discharge not only the bit line, but also the charge coming from the precharge, because those precharges are always on. Now you want to create a differential, so this precharge will delay it. Or you have to increase the size of your memory cell. So not a good thing to happen. So what do? We clock it. What happens? What is the benefit of clocking it? When the word line comes, oh, I'm not even talking about equalizer yet, bhai. Equalizer is the next step. Clocking. When I clock it, what happens? I see that when the word line will turn on, I can now, because now I have a clock control with me, I will turn off the precharge. So the loss of differential that I would experience because of static would no longer be there. Are you with me? Now we talk of the equalizer. Why is this little third transistor in there? जब हमने स्टैटिक की बात करी तो दो ही लगाए थे, जो ही क्लॉक की बात करी हमने तीन लगा दिए. Why do you need the third one now?
One line may be precharged since many clock cycles at one precharge for testing.
So she is saying that one line could have been, one bit line could be precharged over multiple cycles. It was never discharged, but the other bit line might have been discharged just in the previous cycle, and you want to equalize. Why is equalization important?
So it allows us to precharge fast. To read the new data, we have to overcome the offset, which is.
So if I do not equalize the bit lines, what happens? Suppose in the previous cycle, I had written a 0. So my bit line, or written read a 0. my bit line had discharged and my bit line bar had remained at VDD. Now, after the precharge closes, the one which was at VDD was at VDD already, but you have to close the precharge somewhere. All of you know RC delays. And all of you also know that RC delays, what they lead to is that there is an asymptotic charging of capacitances. No capacitance is really fully charged to VDD. You come close to VDD, very close to VDD, very, very close to VDD. But to really come to VDD, you will take infinity. Now, you can't wait for after every cycle for infinity. So what you do, you say, okay, this is the time I'm giving you for precharge. After that, done. So what could happen? Little by little, over multiple cycles, I would be losing 1 millivolt, 0.5 millivolt. After 100 cycles, I might have lost 10 millivolts, 15 millivolts, 20 millivolts. We don't know. Hai? Because we are continuously reading, giving some fixed amount of time to precharge the bit lines. And incidentally, on one particular bit line, I'm continuously reading a 0. So what happens? Now, suppose I want to read a 1. So the other bit line has to discharge. For the sense amplifier now, bit line 1 was already at VDD minus 20 millivolts. Now you start to discharge the other bit line. The other bit line has to now discharge for a longer duration to offset, to compensate the precharge that was pending for the first bit line. Are you able to see this? Huh? Now, as a designer, do you know how many times a bit line would be reading 0 and then after that, okay, at once 1 it would want to read? Do you know? Can you keep a count of that as a designer, memory designer? So you are a memory designer. You have nothing to do with the data. You have nothing to do with the address pattern that the user will give. You cannot do anything about it. It is not in your area of control. So can you let your design just go and fail? No. You want control. You want to say that I, at the end of every cycle, will ensure that both the bit lines are within, let us say, 5 millivolts of each other. But how do you deterministically ensure that? To be able to do that, you have to put this equalizer. Are you able to see this? To be able to do that, you need this equalizer. Now, once you put this equalizer, it also gives you some additional benefit. That additional benefit is that as soon as you turn the precharge on, and let us say after a write cycle, one bit line was at 0, the other one was at VDD. If the equalizer was not there, only one precharge transistor is trying to pull the bit line up. It will take some kind of time. With the precharge on, you have another route from which charge can now come. So bit line precharge speeds up. So an equalizer has a secondary benefit. Primary role of an equalizer is to equalize the bit lines. When someone asks you, why do you want a precharge equalizer? You do not say it improves speed. Yes, it improves speed. But the primary purpose, the primary objective is to equalize the bit lines. Improve speed is a side benefit that you enjoy. Are you with me on this? So clock precharge gives you two benefits, but you design it for the primary benefit. You do not design it for the secondary advantage that you gain out of it. Is that okay? Speed gain. Suppose this particular bit line was, suppose it was discharged to 0 in the cycle because you wanted to write a 0. Okay. Now you turn the precharge on. Let us assume this equalizer was not there. Only this PMOS is helping it getting charged up. But with this equalizer being there, this equalizer also is a transistor which got turned on along with the precharge. And it sees a VDD voltage on this side of the bit line of its on its drain or source, whichever way you want to put at it, and almost ground or a very low voltage on this side. So there will be some flow of charge from here also. So the effective flow of charge to charging up this bit line is more. अरे बाबा, राइट ऑपरेशन खत्म होने के बाद रीसेट तो करना है. So go back to the first thing we discussed in this signal flow. We said that when the clock comes, you turn the precharge off. So in the right cycle, precharge is off. It is at the end of right cycle that precharge will turn on again. That is when I'm talking about. Do you remember? We said clock goes high, internal clock gets generated, wordline gets generated, and somewhere we also said precharge goes off. So that when wordline gets generated, I'm able to create a differential on the bit lines, whether it is for read or for write. So during the read or write cycle, my precharge is anyways off. I'm not bothered about this equalizer being there or not being there. What I'm talking about now in terms of secondary benefit is when I turn the precharge on again, so that my memory gets ready, reset to accept the next cycle. That reset operation will be faster now. My next rising edge of clock can come faster. This is not a benefit on access time. There is a benefit of access time because of equalization. But जो हम write के दौरान precharge की speed को improve करने की बात कर रहे हैं, that is the benefit on cycle time. Cycle time is, or frequency is, when can my two adjacent clock active edges come? Because my precharge happens faster, my next active edge can come faster. Are you able to see this? Is this clear now? Any other questions?
Considering the right of picture for
One is 0, one is 1. I am ensuring there is a full VDD drop between them. But the precharge is off. There is a full drop of VDD across them. You mean to say there is some leakage across them. Yeah, leakage can happen, but you know, it is deterministic, na? Aapne design kara hai. You have designed this, na? So you know, it will be visible to you in every simulation that you do. It is not undeterministic. But look at it, if I did not have this precharge, you have no control over how many clock cycles I had measured or I had read 0 on this side and 1 on that side. You have no control over that. No visibility of that. Do you see that? So now, whatever is the disadvantage, it is in your control. Are you getting it? So as a designer, you have to be a control freak. Nothing in your circuit should happen without your knowledge. Are you with me? Because if something is happening without you knowing about it, then the circuit is going to fail for sure. And it is a hugely expensive proposition. So it's not about someone submitted a wrong paper or a wrong result in some presentation. You can always follow up with an email and say, okay, wo presentation galat thi, correction ke saath le lo. It is not this that we're talking about now. We're talking about millions of dollars of non-recurring expense. We're talking about months and months of product getting launched into the market, getting delayed. Are you able to see this? So as a designer, you have to be in control of what is happening in your design. Even if it means more complexity for you, even if it means more challenge for you in terms of area, power. थोड़ी सी power extra देनी पड़ेगी, दोगे, timing देना, margin छोड़ना पड़ेगा. You will leave that margin. Whatever is required, you will need to do. You will do. But you will still do it like that. Is that okay?
The pre-charging happens after the cycle. It is just inputs and build. You can also assume that because the pre-charging and then get a precondition of bitline with the right drive.
Yes. In fact, in ROMs, you will see that because, okay, look at it like this. In a ROM, there's no risk of loss of data. You also know that ROMs will not be used very frequently. Activity factor is still lower than what it is for SRAMs. So in ROMs, you do not pre-charge at the end of cycle. You actually pre-charge at the beginning of the cycle. But when it comes to SRAMs, you want to be ready when the clock comes. Speed is super important. Okay, and you know that when the clock comes, see, in a memory, you would do reads more often than writes. Now, that may not be the case all times. You will do equal number of reads and writes also, but you may do more reads than writes. So when the read is going to happen, if you're now going to wait for, so clock aa gaya hai, wordline aa raha hai, and you're now waiting for bitline to pre-charge. Tricky situation. You are expected to operate at the speed of the processor. So for all practical purposes, the SRAMs that you will develop, that you will design, you will talk of it as pre-charge happening during reset. Okay? But if you are designing a specific SRAM for a very specific application, where you know that, okay, mera bitline 0 pe rehne se bitline leakage is going to be low. Okay, and therefore you say, okay, bitlines ko I will not pre-charge. In such a situation, you do pre-charge on equalization at the beginning of the cycle. But then your pre-charge transistors will have to be larger because now they are sized for access time also. See, until now, when we are saying pre-charge has to happen before or at the end of the cycle during the reset operation, at that time, you're only impacting T cycle. But as soon as you start to pre-charge at the beginning of the cycle, there's a possibility to impact access time also, TCK to Q. So now you need to really size up the pre-charge and ensure that it happens very fast before the wordline arrives. So unless you are sure that speed is not a concern, access time is also not a bother for you, you would want to pre-charge at the end of the cycle. And you say it is a part of my reset operation, not a part of my access operation. See, if you pre-charge at the start of cycle, you are making pre-charge as a part of your access operation. Access can't happen until pre-charge has happened. When you do it at the end of cycle, you're making it as a part of your reset operation. That access will happen very fast. Okay, next clock may come a little later. At a system level, that means that, okay, after the memory, there is still some margin I have before the next clock will come, and I can put some combinational logic there. Okay, I have something I will put. But if the access time gets delayed, anyways, the cycle time will also get delayed. But I have lesser margin to put combinational logic at the end of my memory. Is that okay? Does that help you? Any more questions? In ROMs, for example, you say that pre-charge will happen at the beginning of the cycle because ROMs are not coupled with the processor directly. They're not expected to operate at the processor speed. Speed is not a very high premium for ROMs. And you say that, okay, if I keep the pre-charge only in the active cycles, then whatever leakage my NOR cell is giving or my NAND cell is giving, that leakage will only reduce. So in ROMs, you'll almost always go for, you may easily go for precharge at the beginning of the cycle. But in SRAMs, you typically would go for end of cycle reset. Otherwise, if there is a very strong need for very low power, and there's absolutely no requirement for very fast access when you want to access the memory, in SRAMs also you can think of precharge at the start of the cycle. Okay?
How can I write things to pen? Suppose I'm writing one other is so these are both
Yeah, so I will turn the precharge off and then I will turn the write driver on. Same cycle. Next cycle, kyun? The same operation, there's a sequence of, so look at it like this. Did I select a word line in one cycle and then read in the next? No. In one cycle itself, word line got selected, bitline got discharged, sense amplifier came, and I got the output. In the same way, in the write cycle, first the precharge goes off, then the word line, then the write driver turns on, then the bit lines get 0, 1, then the word line comes, then you write into the memory cell, and then you close. It is the same cycle. It is just the sequence of operations. State machine. Which state machine you move from this to that to that to that. Is that okay? Clear? So, equalization transistor we have discussed. Next, we look at decoding, column decoding. What you see here is a PMOS-based pass transistor MUX, PTL kind of a MUX, a PMOS-based one. What is the benefit of this? So first of all, are you able to see that this is the MUX? I have select lines which I will generate from the control region somewhere. They will come here. So the lines are already decoded in terms of 0001, 1011. They will come here and they will select one of the pair of these pass transistors. Whichever pass transistor turns on, that pair of bit lines get connected from the array region into the IO. नीचे जाते समय sense amplifier होगा, write driver होगा, whatever is beneath the decoder, it gets connected to them. Is it okay? So, what is the advantage of this kind of a MUX?
very less area.
Density. Just one transistor. आप अगर दूसरा AND और NAND gate वाला MUX बना के दिखाओ, there will be so many transistors you need to handle. Additionally, for those MUXes, you need a full VDD by 2 तक का जाना सब कुछ. You need a full transition. Can you afford that? No.
So it is also a DeMUX as well. It can optically do that.
So this also acts as a DeMUX. If I want to transfer something from bottom to up, it works that way also. याद है मैंने अभी कहा था, for us area is diamond and you want to merge MUX and DeMUX, so this can play that role also. So density आया, speed आया, because you don't need to discharge the bit line to lower than VDD by 2 to be able to sense कि अब 0 transfer करूं कि 1 transfer करूं. That job sense amplifier will do. See, if you put the sense amplifier above it, then you can put that kind of MUX also. But if the sense amplifier is beneath it, you can only need an analog MUX, a pass transistor type of a MUX. You cannot have a digital MUX. Are you able to see this? Because आपका bitline digital है ही नहीं. On the read side, your bitline is not digital at all. So you cannot think of a digital MUX. हम उसको MUX कह रहे हैं, but in your mind, you cannot imagine those NAND gates and select lines going to those NAND gates and doing all that work. Bit lines get connected to the sense amplifier through simple pass gate. What is the challenge here?
Constants can't write.
These are PMOSs. When I want to write, they will not transfer a 0. Are you with me? So you need something else also. Park this thing with you. Now, this was MUX 4. How is it acting as DeMUX? Whatever is on data, it can go to BL now. Depending on which of these two is selected, data can also go up there to the bit line. Pass transistor is दोनों तरफ equivalent है ना वो. So to transfer bitline to VDD, bitline to the data pin, and also data pin to the bitline. Both sides it will do.
Actually, so suppose if you have taken mark 4, so that means that will have 4 words. So if we have suppose 2 bits in one word, so we'll have 2 of these.
Two of these units in different IOs. Yes. So that was why when we said that there is a 72-bit memory, there are 72 muxes there. This unit has to be repeated 72 times, once for every bit. Now this is mux 4. If I have to go to mux 8, what will I need to do? If I use the same architecture, I will have to have 8 select lines. 8 select lines means that 8 wires will run, and then there's only these set of some transistors that I have to place underneath those wires. So my layout is going to be metal limited now. Metal limited layout means you're losing area. You're not being dense. So you need to do something else when you have larger muxes. So what you do is, so यहाँ पे क्या था? यहाँ पे पूरी की पूरी decoding हमने control region में कर दी थी. When the mux is larger, then you do the decoding here. Address and address bar come. Now instead of 8 lines, you have only 6 lines. Are you able to see this? Are you able to see the decoding happening here? Huh? What have you done? You have reduced the area by reducing the number of metal lines. What is the disadvantage? Now you have a stack. Now that bit line, which was a small swing signal, has to transfer through as many address bits you have, as many number of transistors. So you have mux 8, 3 address bits, 3 transistors. You go to mux 16, there will be 4 transistors. Mux 32, there will be 5 transistors. So आप थोड़ा सा differential create कर रहे थे across each such transition. Some differential will get lost. So the delay increases significantly. So what do? This is called tree decoding, because you kind of made a tree there. Okay? What do you do to recover from this kind of a loss? You want better density, but this now takes your speed for a toss. You also want good speed.
You could split it into multiple stages.
So now what we do is we say, okay, we will use a mix of that, some pre-decoding happening in the control region and some pre-decoding happening here. We can call it hybrid mux. So what we could do is for mux 16, we could have 2 stages. First, the lower order LSBs convert 16 bit lines into 4. Mux 4 implement kara. Then MSBs are used in the same manner as the previous slide, and they convert this into 4 into 1. And how many lines would you need? 4 control lines or 4 select lines for the higher mux, 4 for the lower mux, 8. Are you able to visualize this? You needed 1 mux 4 up and 1 mux 4 after that. So 8 bit lines, 8 select lines you will need. If you were to make a tree decoder, how many lines would you have used? 8. मक 16 के लिए आपका 4 एड्रेस बिट्स होता, 4 address bits and 4 address bar bits, 8 lines. So the number of metal lines remains same. and you gain speed.
So, but there is no problem that it will not be able to pass from
Yeah. So so previous slide may I put a PMOS, now I put an NMOS. There you could not have passed a strong 0. Now you can pass a strong 1. So what do you need to do? You need to actually put both PMOS and NMOS on the MUX. Transmission gates. This problem is solved in DVD already, right? So you don't need to ask me. You know how to solve it.
When we get to the multiple stages of process, we have to also use multiple sense amplifiers.
Good question. So Arpit is asking, if I was going to a 2-stage MUX, do I need to add 2 levels of sense amplifiers? Not needed. You could have a sense amplifier. See, once the sense amplifier has come, anyways, once a sense amplifier has come, you have output available in 0 and 1. A sense amplifier will amplify whatever small differential from the bit line you get into a full swing. So once you put a sense amplifier, after that you can have digital logic. Are you able to see this? So you don't need 2 levels of sense amplifiers. What could change is that, okay, now my sense amplifier, what you may still decide to do is, I have sense amplifier before the second stage of MUX or after it. If I keep it after the second stage of MUX, then what happens? I still have to pass 2 pass gates, and the disadvantage of large intermediate bit lines continues, and my read access will become slower. If I put the sense amplifier between the 2 levels of muxing, then my sense amplifier can be triggered faster. The disadvantage is that now I need 4 sense amplifiers. Otherwise, I had needed 1. So it's a speed versus performance trade-off. Are you able to visualize this? Hello? Clear hai? You able to visualize this? That where you place the sense amplifier has an impact on performance and trade-off with area. We already saw that in the first IO slide, but I'm just saying that यहाँ पे भी वो चीज दिखेगी आपको. आप partially भी ऊपर या नीचे जा सकते हो. ठीक है? So we talked about these write assist schemes, and we said that if you have MUX greater than 1, there will be a challenge. Yaad hai? So if you have to use write assist schemes, you can't go for MUX greater than 1 inside the memory array. Then, but you still need to challenge and change the aspect ratio. You could also implement MUX or multiplexing or column decoding in terms of pages. Each page only contains 1 word per row. See, in a typical array, the MUX number of words are there per row. Every word line selects MUX number of words. MUX 4 words get selected. You read only one of them. But in a page architecture, only 1 word per row you can control. Then you can implement whatever write assist, read assist scheme you want. MUX is implemented after the page is done. And the MUXes and the pages can be arranged to meet the aspect ratio requirement that you wanted. Okay? But this has a different level of complexity at the system level. System level means memory subsystem level. कि memory के अंदर आपको कंट्रोल से आपको 2 लेवल ऑफ कंट्रोल्स बनाने पड़ेंगे. एक पेजेस को कंट्रोल कर रहा है, एक पूरी मेमोरी को कंट्रोल कर रहा है. So there is some hierarchical control experience that you will need to bring in. But this solves the problem of assist schemes to be used only with MUX 1, and you still wanting a different aspect ratio for your memory instance. Okay? We'll stop here. We will continue with the IO circuits, specifically the sense amplifiers in the next class. All the best.